Today we are going to discuss about non-ferrous alloys. So up to now we have discussed about what is an alloy and what are all the need to make an alloy, and then we discussed about what is the classification of alloys based on the iron content, and we discussed about the ferrous alloys such as nichrome, alnico, and then stainless steel. And in today's lecture we are going to discuss about non-ferrous alloys, which means the alloys which have iron content which are less. Non-ferrous alloys. So as I told, non-ferrous alloys have composition with minimum or no iron content. So these alloys have minimum say like less than 1% or no iron content. So these alloys are mainly like aluminum alloys, copper alloys, and nickel alloys. So these are the alloys which are less in iron content, and generally they have the properties of the following. So they are usually soft and good in appearance. And they have multi temperature adaptability. So they have low coefficient of friction, and they have low density and corrosion resistance. So these are all general properties of non-ferrous alloys. So in the syllabus we have only copper alloys, and in that copper alloys we have brass and bronze. So these two non-ferrous alloys are there in our syllabus. So first we will discuss about brass alloys. So in brass alloys we have copper and zinc. So these two elements are present in brass alloys, and the percentage of copper varies from 60 to 90%, and the composition of zinc varies from 40 to 10%. So their general property are they have greater strength and durability, and they are easily machinability compared to copper, and their melting points are usually lower compared to copper and zinc. So their melting points are less than copper and zinc. So they have very good corrosion resistance. So we have brass alloys and we have several types. The first one is commercial brass. So it is otherwise called as French gold. So this is the first variety of brass, and in this one we have copper percentage of 90% and the composition of zinc is 10%. So this two combination is called commercial brass, and its properties are it is golden in color and stronger and harder than copper. So these commercial brass are stronger and harder than copper metal, and mainly it is used in jewelries and rivets and making forgings. So these are all the places we can use commercial brass. And the second type of brass is called Dutch metal. So Dutch metal is the second type of brass, and it is also called as low brass. And in this we have copper percentage of 80% and zinc with 20%. So this two combination of copper and zinc is called Dutch metal, and its property mainly it is golden in color as like the commercial brass, and it is good in bending. And its main uses are it is used in making musical instruments, and tubes, and in particular making name boards. So these Dutch metals are used in making musical instruments and name boards in the shops. And the third type is cartridge brass. The cartridge brass is otherwise called spinning brass. So it is otherwise called spinning brass, and here the proportion of copper is 70% and the zinc is 30%, and it is stronger than copper, and it is soft, ductile and harder. Its main uses, it is used in making cartridge cases and condensers tubes, sheet fabrication and etc. So the first type of brass we have discussed here is an alloy of copper, and it mainly contains copper and zinc. So it has three different types of brass. The first one is commercial brass, in which we have copper of 90% and zinc 10%. Dutch metal we have copper 80% and zinc 20%. Cartridge brass we have copper 70% and 30% of zinc, and based on this variation in composition it can be used in different products. The next type of copper alloy what we are going to discuss is bronze alloy. So in bronze alloy we have copper and tin. It is represented as SN. So the first alloy is brass alloy and the second one is bronze alloy, So here, apart from copper, we have tin in the place of zinc. So this is of four kinds. The first one is common bronze. So this common bronze contains copper of 89 to 92 percentage and tin 11 to 8 percentage. So it is mostly soft and ductile and it is durable. Mainly it is used in wires, flanges, utensils and coins. The second bronze metal is gun metal, and here we have copper with 86 percentage and we have zinc 4 percentage and tin 8 percentage, then lead 3 percentage. Its main characteristics are it is hard and it is tough and strong. This is mainly used in heavy load bearings, water fittings, foundry works, high pressure steam plants. The third type of bronze alloy is aluminum bronze. As the name tells, it has copper 90 percentage and aluminum 10 to 7 percentage. This is 90 to 93 percentage and aluminum 10 to 7 percentage. Its main characteristics are it is golden yellow color, it is strong, it's corrosion resistant, abrasion resistant. So this is third kind of bronze, and the fourth type of bronze is nickel bronze. So in nickel bronze you have copper of 90 percentage and nickel 9 percentage and 1 percentage of zinc. Here we have 1 percentage of iron because it is a non-ferrous alloy, so it can have minimum content of iron, so not necessarily 0 percentage of iron. And its characteristics are it is hard and good tensile strength and it is corrosion resistance. It is mainly used in making valves and then bearings and unhardened shafts. So here we discussed about non-ferrous alloys. In that we have either minimum or no iron content. So there are several non-ferrous alloys. In that, aluminum alloys, copper alloys and nickel alloys are the well known. And in our syllabus we have copper alloys, in which we have two kinds. The first one is brass and the second one is bronze. In brass alloys we have copper and zinc, and based on the difference in the proportion of copper and zinc, we have three kinds of brass. The first one is commercial and the second one is Dutch, which is mainly used in making musical instruments, and the third type is cartridge brass. Next we have bronze alloys. In bronze alloys you have the copper and tin, or the two different elements present, and this bronze alloys are classified into four types, in which we have copper and tin alloy with different proportion as common bronze, and the copper and tin of maximum composition, which is called gunmetal. And in bronze, which is aluminum bronze, we have only aluminum and copper, and the fourth kind is nickel bronze, in which we have copper and nickel as the main elements. Next we will discuss about silicon, germanium alloys. So in silicon germanium alloys, as the name tells, it has silicon and germanium. So this alloy can be available with any molar ratio. Of silicon and germanium, which means you have the general formula of silicon 1 minus x and germanium x, which means any molar proportion tells the x can vary from 0 to, like 0.1 to 1, and then the remaining will be the proportion of silicon in that alloy. So throughout the region this alloy is available. You can vary from 0.1 to 1, and this type of silicon germanium alloys are commonly used as a semiconductor material in integrated circuits for heterojunction. So this is the main word, heterojunction bipolar transistors, or it can be used for strain inducing layer in the metal oxide semiconductors. So the main property here, it depends on the lattice constant. So if you want to grow a silicon germanium alloy on a silicon semiconductor, the lattice constant of this alloy and the silicon should be near enough. So lattice constant is a measure of structural compatibility, which means based on the value of lattice constant of this germanium alloy and the germanium, the material can be formed. For example, if I take silicon, So if I say, so this is a silicon crystal. So this is the cubic boxes of silicon. So you have uniform silicon cubes. So this is silicon crystal. So if I want to put on top of it unstrained silicon germanium alloy. So if I want to put this alloy on top of this silicon crystal, it can be done in two ways. The first one is pseudomorphic. So in pseudomorphic, you have this silicon crystal. So this is the silicon crystal. So this is silicon crystal. So on top of this silicon crystal, I am putting this silicon germanium alloy. So if I do that, I will get a structure which is like this, and you can see the silicon germanium alloy, it is adjusted according to the crystal structure of silicon. That means here you have exact square, but here you have elongated values of this structure. This vertical line is elongated, but the horizontal line matches with the silicon crystal. So this type of arrangement is called pseudomorphic. Even though it looks like similar to the silicon, it is actually pseudomorphic because the length of this vertical line is lengthier compared to the horizontal line. So it is no more, it is a square. So this type of thing is called pseudomorphic, or you can match this thing with another format in which again you have the silicon crystal. So this is silicon crystal. So this is silicon crystal, and we want to put this on top of the silicon crystal. What will happen is it will form square and this one will correspond to this thing. So now this looks very similar to this one, but this one is left vacant. Similarly, this type of fit is called misfit dislocation. Here the length of the vertical and the horizontal line will be the same as like the silicon crystal, but the thing is some point will be left as unfit with the crystal of the silicon germanium alloy. So such kind of fit is called misfit dislocation. So the difference between these two is here we have the same equal of horizontal lines, but only the vertical line is elongated. Here you have both the vertical and the horizontal lines are similar to the silicon crystal, but only difference is you have points at that interface which are not fit with anyone. So such kind of thing is called misfit dislocation. So these two probabilities are there when we fix the silicon crystal with the epitaxial growth of the silicon germanium alloys. As a result, what will happen is it will change the band structure. So the band structure is nothing but the energy gap between the conduction and the valence band. So this is your valence band and this is conduction band. So if this is the case for a unstrained silicon, what will happen when we make it as an alloy? It will make a strained silicon germanium alloy. So what will happen is it will narrow the band gap. So as a result, the energy gap between this two, the conduction and the valence band is narrowed down when you make it as an alloy. So this is one of the major success for making alloys. Then finally we have germanium and tin alloys. So in germanium and tin alloys, we will have germanium and tin. But in the case of germanium silicon alloy, you have any molar ratio, which means you can make a composition starting from 0.1 to 1. But in this case, you don't have that full range of composition, because thermodynamically stable alloys are preferred only for a small composition range. So only for small composition we have a stable, thermodynamically stable alloy, otherwise you don't get this alloy. And the main application of the germanium and tin alloy is in the field of microelectronics. So in microelectronics, the main application is due to higher carrier mobility. So higher carrier mobility of this alloys compared to the silicon or germanium pure semiconductors. The second case, it is used in optoelectronics, and in optoelectronics you have tin. If it is more than 9%, it will have direct gap semiconductor. So which means it can be used for making efficient light emission lasers can be fabricated. So when we have more than 9% of tin in this composition, it will have direct band gap. And for example, if you have like germanium of 91 and a tin of 9, this is 9%. And if you have germanium 0.88 and tin 0.12, this is 12%. And germanium, if you have 0.95 and tin if you have 0.05, this is 5%. So in both these cases it will have direct band gap, but in this case it will have indirect band gap. So if you have direct band gap, you have high efficient light emission lasers can be produced. So in today's lecture we have discussed about non-ferrous alloys. In non-ferrous alloys we discussed two types of copper alloys, which is bronze and brass. So brass is alloy of copper and zinc, and bronze is an alloy of copper and tin. And we discussed about various types of brass and bronze alloys. Then finally we discussed about a silicon germanium alloy, an alloy which is used in semiconductor industry mainly in order to vary the band gap between the two conduction and the valence band. So in this case we have more narrowed band gap when we make it as an alloy. And then finally we discussed about germanium tin alloy, which is widely used in microelectronics and optoelectronics. So with this we complete this unit of alloys. So in overall summary, we discussed in this unit alloys, and then the purpose of making alloys, classification of alloys. In classification we have ferrous and non-ferrous alloys, and then we discussed finally today the non-ferrous alloys and their properties and uses. Thank you.